Good afternoon, ladies and gentlemen. My name is Chiravachradej. Today we will learn a new technique on how we can draw shear force diagram and bending moment diagram. Last time we learned how to generate a function or functions, then draw shear force diagram and bending moment diagram according to those functions. Today we'll prove a new technique. We're going to use what they call relationship technique. It actually comprises of two parts. The first part is the relationship between the forces and the applied forces and the shear force. Then we use that relationship to draw the shear force diagram. The second part is drawing the bending moment diagram, where we're going to use the force moment and the shear force diagram to draw the bending moment diagram. So here's the idea. First, we're going to prove the validity of this relationship first. Right? The first relationship, as I discussed, is the relationship between the applied forces, or in fact external forces, which include reaction as well from the support, of course, and the shear force. With that relationship, then we should be able to draw the shear force diagram, and we're going to prove the relationship between the shear force and the bending moment. And if we already have the shear force, then we should be able to draw the bending moment diagram with that relationship. And then I will supplement the knowledge and the relationship, stating the direct relationship between the external moment and the bending moment. Then we'll see example on how we actually draw the shear force diagram and bending moment diagram using these relationships. Okay. Now let's start off with a proof. This is a kind of a beam. Well, we usually use simply supported beam because it's the picture we are familiar with, but in fact it could be any kind of support, because when we look at the proof, it is not involve the support at all. We're going to look at a small element. Now before we continue, I need to discuss about the differences between this picture and the picture in most texts. In this case, what I do is I actually supply upward positive. Therefore, that W, assuming the distributed load, assuming positive, therefore it's going up. Now, in most books, you will see a different picture. The distributed load will go down. However, they will use the magnitude of minus W. Okay, so in fact, it means that if it goes down minus W, it means just go up W. So in fact, it's the same concept, meaning upward positive. The only difference is that I strict with the mathematical size, which means it's going upward positive for now, whereas most of the textbooks look at the weight scenario, meaning they design this for weight resisting. So it's more real application. Therefore, the weight will go, the load will go down. But because they also use upward positive the same way here, which will in the end prove the same thing. Therefore, they have to give that magnitude of minus W. So it just means the same thing going up W. Okay. Now, if we carry on, then we have a small cut. But as I said, we don't want to get involved with the support. So rather than that W apparently has to be 90 degree, meaning if it's in an angle, then we only consider the 90 degree component. Okay. Now, if we look at a small distance on that beam, which we call dx at any position of x, notice that in this case, what I suggest is that it actually doesn't involve the condition of support. It's a general proof, meaning in real life, in real practical example or any problems, it could be any way you supported it. Then we look at that small element. Well, this small element is small enough to consider that W is a straight line function, right? It's just in a very small distance. You know, this fit in the idea that the curvature, if the curvature is come from a small straight line segments, continuous, changing angle. Okay, so this will be the same idea. So if we look at that one, dx is small enough, and we will say it's small enough here because we are the one who choose the size. Well, it is small enough to do the differentiation and the integration. Therefore, it is small enough to make any change in W at that small segment very close to straight line, so that we can assume it is straight line. Of course, on the left hand side, we already know that every time we cut into the material into the application, then we have three unknown forces: the internal forces, the shear, the axial force, and the bending moment. Since we are not, at this moment in time, we are not proving anything zero yet, so we're going to leave it as such. Now, once we move the distance dx, well, we draw the diagram before, we see the picture before. It means that the value of the axial force N, the value of the shear force V, and the value of the bending moment Bm might not be consistent. The word is might not be. It could be in some cases, but this is general cases. We do not assume consistent. We assume that there could be a change. If there is no change, then we prove otherwise later. Okay? Then there we go. Now, to represent the change, now we know the sign convention already. These internal forces always have two sides, opposite side. Okay? So this one here, once we move on, that V and that V plus dV in fact is the same sign convention. One is on the left hand side of the box, or of the cut in fact, and the other one is on the right hand side of the cut. So if the left go up, then the right go down. So in fact, this V and V plus dV is in the same sign convention for shear. The same saying like N and N plus Dn, they both are axial. And the bending moment is smiling on both sides. So that we don't have to cope with the change of direction at the moment. Now, but we, as I said, there could be some changes in the value of all three internal forces. Therefore, once you move from the left hand side to the right hand side, the shear is no longer V, it changes. Okay? Therefore, rather than on the right hand side become V, just V, or we can call it V1, V2 if you want. This one here, however, I think is easier to prove if we actually separate the changes. So on the right hand side it becomes V plus dV. The bending moment become from Bm plus any change dBm. And then of course the axial force become the axial force plus any change. So it's N plus Dn on the right hand side. Once we see this free body diagram, then we're going to use that to prove. So I need more space. I move things around a little bit. It's still the same picture, the small dx element as last page. If we start off, maybe we could start off with sigma Fy maybe. Okay, there. Then sigma Fy equals 0. This is in equilibrium. So all summation of all forces must still be 0. In this case, we consider in the vertical direction. Or in fact, if to be precisely stated, it is not necessarily vertical, but in this case it happened to be vertical. In fact, what we do here is we try to summation of the force to combine all the forces in the V direction, in the shear direction, in the direction of the shear, because now we're going to prove some relationship of shear. Okay, so if we have inclined member shear going that way, it will not be sigma Fv as such, not vertical, I mean. Not sigma summation of the force in the vertical, it will be the summation of in the line of the shear this way. So that sigma Fy signifies the fact that we combine all the forces in the direction, in the line of the shear itself. In that case, we have V, then the first V come from the left hand side going up positive. Wx dx is the total force inside that Wx in the distributed load, and of course it's going up, so positive. And then the last term come from shear on the right hand side going down, negative the whole term. If we separate it out, there we are. Of course we have V and then the distributed load and then minus V. Therefore what we have is dV left. Oh no, sorry, it's minus dV left. Okay, so if I move things around, minus dV onto the side become dV, positive. But because what I want is to find the change in the shear force, therefore I set an equation in terms of the change in the shear force on the left hand side. Okay. Now if we interpret this, okay, dV, as we said, is the change in the shear, meaning the change in the shear value. That one, well, equal is equal. Then the last term is represent the external workload, external load here, total external load there. Okay? In that case, you might start thinking of integration, but at least that term actually mean the total load inside that small element, external though, not internal. It could be from applied load, it could be from reaction, it doesn't matter. But in context, translating the mathematics into English, it is the change in shear is equal to the total external load. We'll mark that for now, because that we're going to use to draw the shear force diagram. This is the relationship between the shear force and the external load. However, it is not directly, direct relationship between the shear force and the load. It is the relationship between the change in the shear force and the external load, which are equal. That external load is not any external load. It has to be external load within the distance we are talking about, because it's only the gap between from left hand side to right hand side. Then that is the first equation or the first relationship we prove here. Next then, because we're going to take moment here, then I will notify point 1 on the left hand side and point 2 on the right hand side here. In this case, if I take moment on the left hand side, well, it will eventually become the same equation, but it's just more complex. Just to simplify things, I would take moment at point 2 instead. Now to take moment at point 2, or in fact to take moment of this body, now we have distributed load. This distributed load apparently is in trapezoid shape. It's not rectangle, it's not triangle, it's trapezoid. Meaning we don't actually know where the centroid is, but we can say specifically from our experience that centroid position should be some distance, some ratio of the distance of the base. For example, the rectangle, the centroid half the base, right? If it's triangle, then the centroid is 1/3 of one edge, or of the 90-degree edge, or 2/3 from the sharp edge, right? If it's parabola, then we have proved some, but it's always in the ratio of the base. So if we say that, well, maybe it's a ratio, k is a constant, well, not necessarily constant, it's a value, right? Which vary from 0 to 1, no more than 1, okay? And then time dx, meaning the x is the base, correct? So this is a kind of a ratio times the base. At this moment in time, the value of k is not significant. So we're going to leave it just that. And well, along the way, we will see that k is not, the value of k is not that significant to the proof. Now, in that case, notice the measurement, because I intend to take moment about point 2, so the measurement, I measurement from point 2 to the centroid. Okay? Now, next then, I take moment about point 2, as we discussed. Of course, the shear at point 2 times 0 disappear. The end, both sides times 0 disappear, both. What we have then, the left hand side, then we have Bm. Well, let's say anti-clockwise positive. That Bm is clockwise, so become negative. That shear times the total distance of dx, and on the left hand side, and then the distributed load. Then the total load is Wx dx, and time the arm k dx. Well, the first term is rotating clockwise, so negative as well. And then the last term from the bending moment on the right hand side, Bm plus dBm. Well, this is all moment about point 2. Therefore, summation equilibrium must be 0. Now we have the term minus Bm, we have the term Bm, then they disappear. Oh, that one, notice in the equation we have dx times dx. What? K dx times Wx dx. Dx is really small. You have dx times dx, which is dx squared. The two very small values times each other. Then the value become the total value of the term, not 0, but it becomes very negligible, very small, so that you don't really have a concern with it. Okay, so we take that out as well, not zero, but small enough to be ignored. So we take that out plus that what I just said. Then we left up with this expression of dBm equal to Vdx, moving Vdx minus Vdx onto the side become plus Vdx, of course. That has two interpretations. Let's look at one by one. The first interpretation is the differential interpretation. That means differentiate bending moment is equal to shear, basically. Now, that has a significance because when you differentiate the bending moment, or any function with the variable, in this case the bending moment is a function of x, right? We already find so many equations with that, so many functions with that. We know the bending moment is a function of x. Therefore, if we differentiate the function with respect to its variable, then we should get slope. But in this case, we have it equal to the shear force. Therefore, slope of the bending moment is equal to the value of the shear. Basically, the function of the slope of bending moment is equal to the function of the shear. So once we draw the shear force diagram, then we should know the slope of the bending moment at any point on that beam or on that structure immediately, because the slope of the bending moment is equal to the value of the shear at that point. So that is the second proof. As I said, this expression dBm equal to Vdx has another term. Okay, this is the same one. Still, I just summarize what we found from sigma summation of all moment about 0.2 equal to 0. Now, in that case, last time we used differentiation form. However, this time we're going to use the integration form. So basically, we integrate both sides. Okay. Of course, if we integrate dBm, then it's from the total value of Bm at 0.1 to the value of Bm at 0.2. So differentiation form limited from Bm1 to Bm2. Okay. On the right hand side is the value of x1 to the value of x2 because it's differentiated with dx. Now, on the right hand side, on the left hand side, of course, it will become Bm2 minus Bm1, or sometimes we call it the difference between the two sides, okay, of the value. Now, so this one here is meaning the change in bending moment, of course, because we measure from 1 to 2. When we use the differences, then we have the change between the two, right? Equal is of course equal, nothing more. Then the last term, we also know that the shear force is a function of x. This has the same effect as integrate y dx. If you integrate y dx, you have the area under the graph of y against x. This one here, you integrate v dx. Therefore, you have the area under the graph as well. However, it's not y and x, it is the shear force with x. Now, the shear force with x is what we call the shear force diagram. Therefore, that one will be the area under the shear force diagram from 0.1 to 0.2. Okay. Of course, the chain of bending moment is from 1 to 2. The area under the shear force diagram is from 0.1 to 0.2 only. Well, if you expand the term, it could be from A to B, it could be from A to C, whatever. Okay? But it must be in the same range. That's what I meant. So that is the third proof. I think in most textbooks they stop here. However, when we apply it, there's some consideration that we have to look at. Okay, so we're gonna keep on. What happened then? If we have a moment, just apply a moment there. Okay, we look at the same thing. We look at the dx, and then we draw the free body diagram again. The same thing, right? Now, if we do, and then on left hand side there is no name. On the right hand side I name it point A because I'm gonna take moment there. Well, you can guess, I presume. Then the first proof, we're talking about the summation of the force first. Okay, there we are. So if we do sigma Fy, notice that then dV becomes 0. On the left hand side you have V positive. On the right hand side you have minus V minus dV, then become V minus V becomes 0, and then minus dV equals 0. dV is 0. What does it mean actually? It means that the moment, when you put in the moment, it doesn't change the value of the shear between the 2 points. Meaning, as we first proved, we only proved that the shear force change with forces. Now it means, directly mean that the moment doesn't cause any direct change into the shear force. Okay, which I mark there. If I take moment about point A, then we have Bm on the left hand side, we have V dV, we have the, V dx, and then we have the moment, the blue moment, the applied moment M. Okay, and the bending moment on the right hand side. The rest of the term times 0 disappear. V plus dV times 0 disappear, N and N plus dN both times 0, both disappear. Therefore, that is the expression. There we are. Now notice that the term V dx, we already coped it, right, in 2 terms, in the differentiation term and the integration term. Okay, so I will ignore that part. I will look at the moment itself. So the chain of bending moment is also equal to the applied moment. Okay, and of course plus the area of shear force diagram under the shear force diagram is, well, just added on. As I said, on this one we only focus on the moment, on the applied moment itself. So that is another comment, not really a proof as such. Well, you can call it a proof. I would think it's just a comment. But there we are. So if we start off with this sign convention, notice that when we prove, we stick with this sign convention all the time. Okay, so if the rest will be true, you need to be fixed with this sign convention. Wx or any forces going up positive, going down negative. Okay, moment, applied moment, clockwise positive, anti-clockwise negative. Shear force has to be that way positive, bending moment has to be smiling positive, and also very important is your x must go from left to right positive. If not, then we might need to prove everything again, or maybe we discuss on how to apply x some other way. Then if this sign convention, this positive sign is fixed, then we have the first proof is that the change in the shear force is equal to the total force applied. If the force is positive, the change, it becomes more, it becomes higher. Okay, so basically it also fixed with sign convention because the change is a kind of slope. If the force is positive, then positive change, meaning the value adding on. If the force going down negative, then negative change, the value of the shear force will drop. The slope bending moment is equal to the value of the shear force. That is the second proof we have. The third proof, we said the change in bending moment is equal to the area under the shear force diagram graph. There we are, the third proof. Okay, and we also proved that the moment doesn't affect the shear force, but just ignore that because it's not really a kind of thing that we have to do anything with. Then the last one is the change in the bending moment. If there is a moment applied, then it's equal to exact amount of that moment applied. Positive to positive, the same. So that is the end of the theory. That is the end of the proof. So with that in mind, let's see what happened. We have this one here. Example 1. Point load, bending moment, and then distributed load. So let's see how we're going to draw shear force diagram and bending moment diagram using the new technique we just learned. In this case, we need all the forces acting on the beam to be able to draw the shear force diagram correctly. So we're going to find out all reaction first. The usual way to find all reaction, then you just draw the general free body diagram to find reactions. Right? Therefore, in this case, we can do sigma fx, sigma moment, and sigma fy, or sigma moment about 0.1, 0.2, depending on your style. But in the end, anyhow, we should end up with the value of R1x, R5y, and R1y as shown. Once we know that, we're going to use this information to draw the shear force diagram. Now, to be able to do that, then let's look at, this is the free body diagram, right? Because we need all the forces to draw it. Therefore, it would be helpful if we can see the forces while we're drawing it. So these are all the forces. Now, like the usual way, when we draw the shear force diagram, we start off using the whole beam or the whole structure. In this case, the whole beam from point 1 to point 2, 3, 4, and 5. Now, before we enter point 1, we are on the left hand side of the beam. We are not on the beam yet. There is no shear force there. Well, or at least not shear force that we're concerned with. So the shear force of the beam outside the beam is 0. It doesn't exist. Now you move on to point 1, then you were hit not by 36. 36 kilonewton is not 90 degree. When we prove the shear force, we use 90 degree forces, or in fact the force on the same line F, the shear. So 90 degree to the beam in this case. Therefore, it is that 80 kilonewton. 80 kilonewton going up, we say it's positive. And the change of the shear force is equal to that force. Therefore, from 0, change increased by 80, it becomes 80, right? Not exact value, don't forget not exact value. Now, from point 1 to point 2, there is no force between point 1 and point 2. Therefore, if there is no force, then force is 0. If force is 0, the change in the shear force must also be 0, meaning, of course, no change. There we are. So it's 80 all the way through between 1 and 2. Then we hit by that 60 kilonewton, but that 60 kilonewton is not 90 degree. That 60 kilonewton has two components. One is vertical, one is horizontal. The 90 degree one is vertical. Therefore, it is that 60. Therefore, it's 60 times 4 over 5. 60 times 4 over 5 is 48, right? Now it's going, that 90 degree going down, meaning the change must be negative, must be reducing. Again, it doesn't reduce to 48 or minus 48. It is the change that is equal to minus 48. So you have 80. You change by minus 48, so it becomes 80 minus 48, and the value becomes 32. Now, next, once we have that value, notice between point 2, 3, and 4, there is no forces. There is only one moment applied there. But we already proved that the moment doesn't disturb the value of the shear. The applied moment does not disturb the value of the shear. Therefore, we ignore it. And there is no force, therefore no change. No change meaning it's a constant, therefore the whole line there. Next, then, between 4 and 5 is no longer a point load. It is 75 kilonewton per meter, meaning 1 meter it changed 75, 2 meter it changed 150. If there is a 3 meter, it changed by 225 kilonewtons. Therefore, notice, since every single distance is reduced by the same amount, this is a straight line function. Therefore, it reduces down as such. 2 meters, 1 meter 75, 2 meter 150, going down minus, right? So it reduced down there. Reduced by how much? Reduced by 150. So the end, again, the value is not equal to the force. The force is not equal to the value of the shear force. The change in the shear force is equal to the force. Therefore, that point there is not minus 150 because we already have 32. 32 then reduced by 150, we have minus 118 left. At point 5, there is that 118 kilonewton pushing up. From minus 118 kilonewton plus 118 kilonewton, it becomes 0. Therefore, it closes down here as such. So that is the shear force diagram. Okay, and how do we find that distance? Don't forget, this is the same technique to draw the graph. If there is a cut 0, if it passed 0, you have to tell where 0 is. The idea is simple. We start off with 32 kilonewton, 1 meter drop by 75. So if you're gonna become 0, meaning you have to drop by 32. If you know 75 1 meter drops 75, then you can find out how many meters drop by 32. Taking simple ratio. Okay, so there we are. That 80 causing the first rise from 0, then jump up third 80. That one is not 60 because in fact it has to take the vertical component, in this case 4/5, then the change is minus 48, not the value is equal to 48, the change is minus 48. You have 80 minus 48, 32, then no change, and then that one there. And then of course the last step, it push up back to 0. So that is how we draw the shear force diagram with this technique. There's no cut section and find equations here. Now, to draw the bending moment diagram, we need both of them. We need the shear force diagram and we need the free body diagram. The shear force diagram so that we can calculate the area under the graph. The free body diagram so that we can see all the moment applied. There we are. That is again the beam. Start off 0. Okay, before point 1, everything is 0. Then hit 1, there's no moment applied, there's only forces. But forces does not change moment. Therefore, it stays still. At point 1, it is just 0, staying at the same place. However, between 1 and 2, we have the shear force diagram. The shear force diagram, the height is 80, the width, the base is 1. So the total area becomes 80, that area there. Therefore, because this 80, the shear force is consistently 80 between 1 and 2, and we also prove that the slope of the bending moment is equal to the shear. If the slope is consistent, then the graph is a straight line. Therefore, that is a straight line, okay, coming up. Next then, we calculate the area between, that is 80, the area is 80. Therefore, changing from 0 to plus in 80 become 0 to 80 kilonewton meters. The next then between 2 and 3, okay, that is the area we have to look at. There is no moment at point 2, so there is no jump here. Okay, there we are. Again, 32 all the way through, 32 kilonewton all the way through. Shear is consistent. If shear is consistent, is equal to slope of bending moment. Therefore, slope of bending moment is also consistent. Therefore, it's still a straight line here. 32 times 1.5 is 48. Now, the value again, the value of bending moment does not equal to the area of the shear force diagram. It is the change. The change in the bending moment is equal to the area. Therefore, it is changing by 48, not become 48, but it changed by 48. Therefore, it becomes 80 plus 48, 128 kilonewton meters. Then we hit with that 90 kilonewton meter. That one on the right hand side, the applied moment. That applied moment, when we set it out, it said that clockwise positive. This one here is anti-clockwise, therefore negative. If the change is equal to negative, then the value drop. There is no distance, it is just happened at that point. So when it dropped only at that point. From 128 drop by 90 become 38 kilonewton meter at that point. To the right hand side of point 3 basically. Then from 3 to 4, we go there, the area again straight line function, consistent slope. That one, and then calculate the area, 48 again, become 86. Now this one is a tough part. Not a tough part, it's a part that we have to consider. Because the area between 4 and that cut 0 point is one area. Okay, notice the slope. At first, at point 4, the slope is quite high, positively high, and then become reducing. So the curvature increase quickly and then slowly, and then become at a peak at where the slope cut 0 or the shear cut 0, the same point. And then after that, the slope reducing slowly, and then at the end reduce quickly. Therefore, it becomes that shape. Okay. Then in this case, we have to look at two areas altogether. There we are. That area there is equal to the triangle area. Calculation is on the top. combined to what we already have, then we have 92.83 kilonewton meters. And then the last area, the area is about, well, 92 minus 92.82, well, it's negative, right? So reducing. This one here is not increasing, reducing. Then combine what we have, 92.83, the top, the area is 92.82 approximately. The last decimal point is also, it can be round up error. And in this case, we accept it as close down as 0. Summarize, there we are, no change there. And then the area take part. Then that drop by the applied moment. The area positive again, going up. This area here is not a rectangle, meaning the value is not consistent. The value of the shear force is not consistent. If the value of the shear force is not consistent, the value of the slope of the bending moment, which is equal to the shear, must not be consistent either. Therefore, the slope is no longer, the slope of the bending moment is not a straight line. In this case, it's a parabola. Okay, and the last part, and end up 0. And to summarize this example, there we are. So the idea will be changing from finding equation and then draw the graph from the equation. We use relationship from the free body diagram and the forces to draw the shear force diagram. Then we use the shear force diagram, which we just construct, plus the moment on the free body diagram combined to draw the bending moment diagram. That's the whole idea. Now, example 2 then. Okay, this one here is the same as last lecture for the comparison, of course. The distributed load again is not 90 degree, so the one that we use will be the the vertical one, which means 4/5 of that 120. Okay, but the same idea start by finding reaction first. General equation, general free body diagram, sigma fx, sigma fy, sigma moment, 3 unknown, 3 equations. We can solve all 3 unknowns reactions. Once we get all reactions, then that is the total free body diagram. Now, the shear force diagram, then the first step is the same. Before we enter, there is nothing, right? 0. Therefore, once we hit point 1, I calculate this first then. Because we know we're going to use the component of 4/5, therefore we calculate it first, which is 96 kilonewton per meter, the whole length. This is the vertical. I have to emphasize the horizontal component doesn't disappear. Okay, doesn't disappear. It's still there, and we are just not adding it in equation because we only look at the vertical part of it. Okay, the first one then, when we hit from outside the beam or 0. The value doesn't exist, no beam exists yet. Then hit point 1, the force we look at is the 90 degree. In this case, there we are, the vertical one. The 145 from 0, then we add in 144, that one go up by that. And then, because we already know that it's going down by 96 kilonewton per meter, then for 4 meter, we can calculate the total change. Because it's always 96 kilonewton per meter, meaning the value of change, 1 meter always change 96. If the change is consistent, it is a straight line function, so we'll draw a straight line function downwards. The total change is in 4 meters. 1 meter 96, 2 meter 192, 4 meter then 384. And then we calculate, we know that at the beginning we have 144, then it changed by 384. So 144 minus 384, then we can calculate that bending moment at point 2 minus 240. Then the force 432, then we hit, we find out where it cuts 0 first. Sorry, I jumped a step. Now again the same idea, 1 meter it changed by 96. It changed from 144 to 0, meaning you change altogether 144. So we can work out that is 1.5 meters. There we are. Then the one go back to the shear force at point 2. The 432 push up. Therefore, it become that 2 minus 240 plus 432, 192. There we go, it jump up there. And of course the last part is going down there again, 96 kilonewton per meter. Every 1 meter, 96, straight line function. There we are. And then of course at 2 meter, the total change is 192. And we already have 192, reduced by 192, it becomes 0 at 0.3. There we are. So that is shear force diagram. Okay. The bending moment diagram then, because there is no moment applied here on the body at all, no matter what the support or at the middle of the body. So in this case, since there is no moment on the free body diagram, we can ignore the free body diagram then. There we are. Okay. So because there is no external bending moment, as I said, the bending moment only change with the area of the shear force diagram. There we are. So the shear force diagram on the top, then the bending moment there. First point remains 0. Come in, no moment apply, so still 0. Now the first one here, if we hit, is the rectangle. The slope is not consistent because it's the value of the shear force change, meaning the value of the slope also change. So the change in bending moment will not be a straight line. Now the way we look at it is that at the beginning, the value of shear force is 144, and then in the end it becomes 0. Meaning at the beginning, the slope is higher than at the end. So therefore, if the slope is high, the change is quick. Therefore, the graph of the bending moment will be steeper, and therefore it becomes in that shape. Oh, hang on. The area is 108. Okay, change from 0 to that point, then become 108 kilonewton meters. And the way we draw the graph, again, as I said, notice the going up at the beginning, the slope is quicker, therefore it becomes sharper, steeper, and then reduce the slope until on the top, where the slope is 0, it becomes a horizontal line, well, or it is meant to be. And then of course that area there, the area is equal to 300. Okay, but this one here is the slope is become minus. The shear force is minus, therefore the slope of the bending moment on that part is also minus. If the slope minus, meaning it's reducing. Okay, and therefore that 300 is a minus value. Again, the area of the shear force diagram does not equal to the value of bending moment. It is the change of bending moment that is equal to the area under the graph of the shear force diagram. Therefore, it becomes 108 minus 300, because at the beginning of that session, then we have 108 to start off with. Okay, and then the change, notice, at 1.5 meter, it is small negative. Well, at first it's 0 and then it's small negative, meaning it reduces slowly. At the end, it becomes minus 240. The slope becomes a lot more negative. Therefore, it reduces quicker in the end. And the picture is that way. Now we also have another cut 0 here. Okay, there we are. So we assume that it cut 0 at the point of resistance x. Okay, and of course the height of that shear force diagram at point x is equal to cx, because it's a straight line function. C is just any constant times x. Okay. Therefore, using similar triangle, then we know that 144, the triangle on the left hand side, or can use the right hand side, is the same ratio. Okay, so we have 144 over the base 1.5. Okay, for the base of x, then the height is cx. So on the other side, cx over x. Then we can work out the value of c, 96. Now to calculate the area, then we use, because it's triangle, correct? To calculate the area, then we have 1 over 2 times x times the height cx, which is 96x. Then if we want to reduce from 108 to 0, meaning it reduced by 108, correct? The area already in the negative side, so we ignore the negative value, and apparently it worked out to be 1.5 meter. There we are. No, but since 1.5 meter is measured from cut 0 point, If we're going to measure it from the support 1, then it comes 1.5 meter first, and then another 1.5 meters, or combined 3 meters. The last part is that triangle. At the beginning, it increased quickly. In the end, it increased slow, well, almost not increasing, it's become 0 at 0.3. So the bending moment will not increase at 0.3. Okay, there we are. So the area is 192. We already have minus 192. Then it becomes 0. But at the beginning, it increased quickly. At the end, it increased slowly. Therefore, it is in this shape. And that summarizes the two diagrams for the second example. And that actually concludes the lesson for today. So, today we learn a new technique on how we can draw the shear force diagram and bending moment diagram. Meaning at this moment in time, we should be able to draw the shear force diagram and bending moment diagram with two techniques. The first technique is to find the function describing them and then draw the graph according to that function we found. The second technique is to use the force, the external forces, reactions and applied forces to draw the shear force diagram. Then using the shear force diagram and the bending and the moment on the free body diagram to draw the bending moment diagram. And the rest is up to your practice then. This is still a graph, therefore everything that you should tell drawing a graph, you should still tell. The peaks, the value at the starting point, the value at the end point, the peaks where it cuts 0. The whole thing must be told, including the sign convention. This one here, the main difference, in my opinion, is that you don't have the liberty to say which way bending moment is positive, which way x is positive. Everything is according to the fixed sign convention, whereas the equation you could tell in the graph, you could adapt to the way you see it. You make it draw easier in many cases. Okay, but anyway, as I said, the rest is up to your practice. So hopefully, I hope you enjoy the lesson today, and I see you again next time. Thank you very much. Bye-bye.